Hey folks, today we're talking about the properties of limits. So last time we got into what a limit is, so we should be applying some of those ideas that we talked about in 1.1 and at the end of pre-calculus into some of the tricks that we can go through when it comes to looking at a limit. So all the limit properties are pretty much exactly what your math voice, your math instincts would say that you should do. So for instance, if you have the limit of two functions that are added together, you could take the limits of them individually. And then you could also do that with subtracting. So that's all this is talking about here. So if I wanted to figure out the limit of two things added together, I would figure out the limit of the first thing, figure out the limit of the second thing, and then I can add those results together. Pretty straightforward. This isn't exactly confusing or anything, but you can take any constants out in front of limits. So I could take this from here, and I could bump it out in front, and that's where they get the k in front of the limit. So the limit of a function times a constant, well, figure out the limit of the function, and you could still times it by the constant, either to the function or to the limit at the end, so it doesn't really matter. Multiplication is the limit of the product is the product of the limits. Same thing with division. Exponent, this is kind of the maybe kind of thinks of your exponent rules or your log rules, is that if you've got the limit of something to a power, you can do the limit of that something and then raise that result to a power. And then the last one is probably the only tricky one that that you're going to see. The limit of two functions getting composed. So I'm taking the limit of f of g of x. What's weird about this is you have to take the limit of the inside function first. So I'm going to take the limit of the inside function. That's going to give me some number, and then that becomes my new limit. There isn't a great way to write this up, but I'll try my best. So in this scenario, what I would calculate first is the limit of g of x as x approaches some number. Now that limit, why did I do that first? Because it's the inside function. So you think of the order of operations, you do what's in the parentheses first, right? So I take the limit of that. That's going to give me some limit, some answer, which we would call L. Then that would lead me to being able to calculate the limit of f of x now as x approaches, and it's going to turn out that it's going to be approaching that new value. So this thing ends up becoming the limit of the g function ends up becoming what x approaches for the f function. And we'll get into some examples about that. I think there's two that I can think of off the top of my head in the notes, or maybe it was in the homework. Anyway, so let's say you have the limit of this function. This looks like something that would be crazy to try to figure out what's happening at a... All right, folks, sorry, I don't remember where I left off, so I might be repeating myself a little bit here. So we've got all of our limit properties. Like I said, most of them make total sense, kind of your math instinct. You follow your instincts and you'll be fine. The only one that's kind of tricky is when you compose functions. It's just kind of weird. You got to do the limit of the inside, and that answer becomes the new x value that you're approaching for the outside function. This is the outside function. This is the inside function. So as you look at this, looks like a super complicated limit, but it's actually not as scary as it looks. You know, you would just evaluate this limit and the limit of this, the limit of that, square root this. Just a quick notation thing here. Remember that this is kind of what we did with sine. Remember how we used to write sine squared? This means g of x, and the whole thing is getting squared. That's just a little notational idea. There is a little bit of sneakiness when you're using these properties for a general two-sided limit, and you encounter DNE, you must split up into left and right hand limits. So it could be that the general limit still applies. This is one, I think it shows up once in the homework and maybe once in the notes. It's one of those things that I think Corpy put it in there to make sure that, you know, he wants to cover every detail that might show up on the AP test. This is not one that I remember seeing a lot of. All right, so let's give it a try. Actually, I'm going to pause here. I'm going to encourage you to pause here without me even showing an example and see if you could do this one. Let's see how you did. I mean, like I said, it's so straightforward. Just follow your math instinct. So this would be the same as 2 times the limit as x approaches 3 of f of x is 8. I'll write it out. I'll write it out the long way once. The limit of f of x as x approaches 3 minus 4 times the limit of g of x as x approaches 3. So that's if I was applying my properties. This is my rewrite. We now know that the limit, or so it was given that the limit of f of x as x approaches 3 is 8, minus 4, the limit of g of x as x approaches 3 is negative 2. So we would get 16 plus 8. 16 plus 8 is 24. Let's see if you can rewrite this one. Nah, never mind. I'm not even going to make you rewrite it. Go ahead, pause, try to do that one. Let's see how you did. This would be the same as 2 times, what they say the limit of g of x was, negative 2. Make sure that you put that in parentheses, because that's going to be 4. Oh, bad math, Mr. Stuckey. Oh, the whole thing is getting squared. So this would be 2 times negative 2, and then getting squared. So that would be negative 4 squared, which would end up being 16. Ooh. My bad, but I caught it. All right, last one's yours. Pause, go get them. Let's see how you did. So this would be the cube root of, what's the limit of f of x? 8 again, over what's the limit of g of x? Negative 2, plus 4, times what's the limit of h of x? 0, I like that. Oh, this is interesting. What would you put in for x? Remember, these are all limit values, but this is the x value that you're approaching. So you can just direct substitute that. So I would get the cube root of 8 is 2 over negative 2 plus 4 times 0 is 0 over 10. That would be negative 1 plus 0, which would be negative 1. So we can apply this same idea. We can apply it to limits that are done graphically. So now I'm giving you the graph of f, I'm giving you the graph of g, and you're going to calculate the limits based on the graph. So we would look and see where the values are approaching based on the picture. So this would be 2 times, I'm going to put it in parentheses right away so I don't make that same mistake. Okay, what's the limit of f of x as x approaches 0? So as x approaches 0, what are my y values approaching? They're approaching 2. Plus 3 times g of x, what is the limit? What's happening to g as x approaches 0? From both sides, they are meeting at a height of 0. Now, if this is a free response, you can stop here if you want. You can actually be done. Stop if free response question. If this is a free response question, you don't have to go any further, but it's most likely this would not be a free response because it's too easy for a free response. So you would most likely clean this up so that you could check the multiple choice answer, and we would get 8 plus 0, which is 8. Okay, let's have you try the next one. Pause, give it a whirl. Okay, so x squared, well, that's my function, that's my x value that I'm approaching. I can direct substitute negative 3 in for x, and then I square it. What's the limit of g of x as x approaches negative 3? 1, negative 1, negative 2, negative 3. That's approaching a height of 1. Over f of x. This is my f of x function as x approaches negative 3, 1, 2, negative 3. Looks like it's approaching a height of negative 1. So we would clean that up. What's that? That's 9 times 1 divided by negative 1. That'd be negative 9. What's the limit? Oh, this is the crazy one. All right, good. I'm glad we got one of these. So let's go. We're going to do the inside limit first. So that's the limit of f of x as x approaches -3. That's what I mean by inside function. It's the one inside the parentheses. So f of x has a limit of -1 as x approaches -3. Now we're going to take that limit, and that answer to the limit becomes what x approaches for f of x. So now I'm going to do the limit of g of x. I think I said f of x. The limit of g of x as x approaches -1. I want to draw a little arrow here to point out where this came from. This answer becomes this limit. So I get this as my limit. X approaches -1 for g. Now, is the point? Where's the point? The point is up at 2, but the limit is what the graph intended to do. And our graph clearly intended to meet at a height of 1. So our answer would be +1. Pause and think through that one again. If that's a little sneaky to you, hit rewind and talk through that one again. All right, let's see. So this is pretty straightforward. This is, I can plug in -1. -1 squared is 1. So what's happening? This is really saying what's happening to my limit. What's the limit of g of -1? Which, by the way, as x approaches, I don't like how I wrote that. I can just direct substitute into this. The limit of g of x squared as x approaches -1 means that I can just plug -1 right into this. So I would get -1, which turns out to be -1 squared would turn out to be g of 1. Well, what's g of 1? If I go to 1, g of 1 is -1. So this is saying what's happening to my function as x approaches -1. Well, that means I can direct substitute -1 in here, and I would get -1 squared, which would be 1. But then I would be asking you, what is g of 1? G of 1 would be -1. That one's a tough one, too. I didn't think that one was as tough as it is. But trying to explain it, at least it's tough to me trying to explain. I think this one's a little easier. 2 times, okay, what's f of x as x approaches 1? From the left, that little minus means from the left. So from the left, f of x is approaching a height of 2. So 2 times 2 over. This is a group. 1 from the left is -1. But we're squaring it. That's 4 divided by 1, which is 4. Let's see here. Let's go with a gray. All right, so now I'm going to direct substitute any of the x's that I can, and then I have to evaluate the limits for any of the function values. So this is going to be 5 minus, I can input -1 squared in for that, times 3 plus, what's the limit of f of x as x approaches -1 from the right? So -1, here's f of x, there's -1 coming from the right, that's at a height of 2. And then all of that is underneath the square root. So I would get 5 minus 3 plus 2 is 5. -1 squared is 1. 1 times 5 would be 5. So 5 minus root 5. And then lastly, all right. Oh, yeah, these are super. I love these. As x approaches 2, from the left, no, as x approaches 2 for f of x, no, I don't love these. Dang it. This is dne times the limit for g as x approaches 2 is 0. Now, I'm thinking the answer is still going to be 0. Or dne, I mean. Sorry, dne. But we got to double check. And the way we double check is we look at the one-sided limits. So this is an alert. This is something that we've got to, that takes a little bit more thinking than the other ones did. So now I'm going to take the one-sided limits. So the limit of f of x as x approaches 2 from the left times g of x. Okay, so let's see. So coming from the left, as I approach 2 from the left, I reach a height of 1 times, as I approach, that's 0. 1 times 0 is 0. Then we're going to try it from the other side. So the limit as x approaches 2 from the right, f of x times g of x. Limit as we approach 2 from the right would be negative 1 times 0, which would be 0? Wait a minute. I'm going to have to do some more work on that one. I'm going to have to do some more work on that one to see if that's true. So right now, the overall limit is not DNE. The overall limit is 0. I'm going to double check that. So ask about that one in class. That's interesting. I guess because it's 0, I guess that would probably be true, because all these values, as I multiply this times something close to 0, it's getting closer and closer to 0. I think that's true. I think that works. That's a surprise. All right, what do we got? Oh, this good old squeeze theorem. This is one of the best theorems because it's so straightforward. It makes total sense. The squeeze theorem. Now, this is the real reason I think we teach this at this point, not because this is a great theorem, but it sets us up to talk about how to make our arguments, how to make an argument in mathematics, how to make a proof, kind of, as if you want to think about it. So, if g of x is less than or equal to f of x is less than or equal to h of x. So what this is really saying here is that f is squeezed between g and h. That means that every y value of f is going to be smaller than every y value of h, and every y value of f is going to be bigger than every y value of g. So all those values are trapped in between those two functions, except possibly at c. And the only reason we throw except in there, because there might be a hole somewhere. And if you have a hole, is that going to change your limit? Holes don't change limits. Remember, the hole would just take away the bridge. The two roads would still be leading to the same place, so you would still have a limit. They're headed to the same place. There just wouldn't be a hole there. So that's why we have to take this except piece in there. Okay, so if f is squeezed between the functions g and h, and we know if the limit of g as x approaches c and the limit of h as x approaches c is the same number, then those two limits will squeeze f to have that same limit. So here's a way to think about it. Now this isn't a great example because the one I'm going to draw, g is less than f to begin with, and then it becomes bigger than f, but at least gives you a kind of a basic understanding of what this looks like. So you would have this one curve coming in. Here's the curve. Let's call this curve g of x. You've got this other curve. Let's say this other curve goes this way. This is what we would call h of x. And then the curve for f of x falls somewhere in between these two things. So f of x is somewhere like goes up here, then squeezes in between there, and then comes out here. This is the graph of f of x. Now the value that we're talking about, the piece that we care about, is right here. This is where c is. That's the point x equals c. And so you get the idea, like all sorts of craziness can happen to F, but as it gets closer and closer to being trapped in between those two, it gets squeezed in to that spot. So whatever H is doing and whatever G is doing there, as long as they're doing the same thing, which is what this limit says, then F has to be trapped. If these two limits aren't the same, if the limit of G and the limit of H aren't the same, then you can't guarantee that the F function would be trapped in between those other two. Okay, so how do we prove this? I think that's probably the idea, that's enough of an explanation. Once you see in a couple examples, it really, I think, starts to make a lot more sense. So let's try to prove that if negative 3x is less than or equal to g is less than or equal to x squared plus x plus 3, then find the limit of g of x. Well, we know nothing about g of x except that it's trapped between these two curves. That's all we know. So we're going to use that as our sort of beginning point. So number one, I like the way I wrote it up in the homework, so I'm going to go grab the homework. Number one, I'm going to find the limit of one end of my functions that are squeezing the other function. So I'm going to find the limit of negative 3x as x approaches negative 1. Plug in negative 1, we find that that limit is 3. Now I'm going to do it and I'm going to go again, I'm going to find the limit of the other function as x approaches negative 1. That would be negative 1 squared plus negative 1 plus 3, which ends up being 3. This is what Corpy calls these the bread. So he calls the top and bottom pieces of the bread separately. He calls these the bread, and then he calls this the lunch meat. And so you're proving that the pieces of bread are the same. So now we've proven that the pieces of bread are the same. They gave us that g of x falls between these two. So now we just have to make a nice little write-up. So number 2 would be our write-up here. Since negative 3x is less than or equal to g of x is less than or equal to x squared plus x plus 3, and the limit of negative 3x as x approaches negative 1 is equal to 3, which is equal to the limit of x squared plus x plus 3 as x approaches negative 1. Then, okay, so let's stop there and see if this makes sense. Look what we've done so far. I've established that the function, or they gave me, but I've established that this function falls between these two other functions. And I've shown that the limits of those other two functions as x approaches negative 1 are both at a height of 3. So what does that then mean about the limit of g of x? It means then by the squeeze theorem. So you always got to reference the theorem that you're using. We're using the squeeze theorem here. So by the squeeze theorem, the limit of g of x as x approaches negative 1 must be 3. This is what an answer looks like. That's a nice little argument that we've made. We've shown that g falls between these two. We've shown that the limit of these two is 3. So then, referencing back to the squeeze theorem, the theorem that we're using, we can say that we know that the limit must be this. So like I said, there's a couple of chances to practice this on the homework. So the tough part is you're going to get used to this write-up. Right now it's going to feel a little bit weird, but you guys will get used to it as time goes on. Good luck.